You're live.
Hello, everyone. Thank you very much for joining us after our brief hiatus. This is Matthew, and Alexander is behind the scenes, and Professor Impey will take it from here, and we'll get started with questions.
Okay, thanks everyone. Yeah, we took a little break. Matthew's on holiday. I don't get to go anywhere. All my travel's shot for the year. It's quite sad. I was due to get back from Italy today, I think, from a month there. That didn't happen. Oh well, no crying over spilt milk. I'm sure it's the same for everyone. Floor is open for your questions on astronomy.
The very first question is from Malik, who would like to know, all the elements which we have on Earth and which we are made of, did they come from the sun?
No, good question, but these elements were pre-existing because first of all, remember that the sun and the solar system all formed contemporaneously at the same time from the same cloud of gas and dust. And so in that process, the sun collapsed at the center to become hot enough for fusion to occur, which is 10 million Kelvin. And it pretty much usurped 99.9 and a bit % of the solar nebula's mass. And the remaining residue of gas and dust left over formed a disk, which eventually turned into planets after about 50 million years. All of this 4.54 billion years ago. So the planets and us, by extension, formed out of material that was part of the solar nebula and part of the same gas cloud that formed the sun. The sun is 99.9% hydrogen and helium with very trace amounts of heavier elements. The periphery of the solar nebula, where the temperatures were cooler, allowed particulates to condense into grains and crystals and then aggregate by electrostatic and then gravity forces into planets, asteroids, etc. And so that's why you end up with material that's concentrated in heavier elements at the periphery of the solar nebula. And that's how you end up with planets and carbon-rich material. So since all of those heavy elements, even though they are a small percentage of the overall solar system, most of which is the sun, and the gas giants, of course, are mostly hydrogen and helium too, those heavy elements were built into the solar nebula. So they all were formed earlier. And essentially all the heavy elements in the carbon, nitrogen, and oxygen that life depends on in our bodies and other living creatures, the silicon, iron, etc., and the Earth's crust, were formed in the cores of other stars, distant stars, long before the solar system formed, probably, and certainly at least 4.5 billion years ago. So it's an interesting story, the story of our atoms. They came from a variety of sources. They came from, you can't tag any of the atoms to give their specific stories, but they undoubtedly came from generation upon generation of stars being born and dying and ejecting their material or their residue into space to become part of another generation of stars. And in that process, in the Milky Way, over 11 billion years, a lot of heavy elements seeded space before the solar nebula formed. So our atoms that make us organic material and life have had an extraordinary history through stars over cosmic time. The heaviest elements, the ones above iron, stars are able to make iron fairly easily, but it's the most stable element. After that, energy is required for the fusion to take place. And that typically comes in violent places like neutron star collisions and supernovae. And that's where we think most of the heavy elements and precious metals like gold, silver, platinum came from. So it's a long and complex story. But basically, the heavy elements that we are made of and the planets are made of all were created more than 4.5 billion years ago in other parts of the Milky Way.
All right, the next question is from Manmeet Bhushan, who's on with us live. Is a star a solid object or just gaseous? What does it sort of feel like? Could you touch a surface? Is it thick? Like, what is the nature of it?
The star is technically a fourth state of matter beyond solid, liquid, and gas. The fourth state of matter to physicists is plasma. So plasma is essentially a gas, so it's low density, and it's very hot, which means the electrons have been stripped off the nuclei. And so it's a plasma is a low density, rarefied, hot medium where the nuclei, which in general are protons, because most of the material is hydrogen, the simplest element, and the electrons are separated from each other and just whizzing around at very high speeds, relativistic speeds. So that's what the sun is made of, a plasma that's mostly hydrogen and helium. And the density of it is actually quite low. So at the part of the sun that we see as the edge, the photosphere, which is the place where the density is low enough for radiation to travel freely to our eyes and taking 8 minutes to do so at the speed of light, the density is very low, hundreds, maybe thousands of times less than water. So it's a very low density gas. As you go towards the center of the sun, temperature, density, and temperature all increase. And there are parts of the sun that are under such intense gravity that they're actually denser than normal liquids or solids. That's a pretty interesting situation. But even there, it's still a plasma. It's still a place where there's no structure to the atoms. They are whizzing around, colliding with each other every second.
The next question is from Wolf and Bree, who's on with us live. Scientists have recently discovered microbes that are supposedly over 100 million years old. How could this be possible?
Yeah, I've seen that article. It's an important article about astrobiology. The recovery, so their microbes are undersea and underground microbes that live in situations where they have to go into a wait state, essentially hibernate. And there's often been a question in astrobiology whether microbes that are in extreme situations, where they're starved of energy or resources, can actually go into suspended animation. And this discovery is a claim, not yet verified. It's a fairly bold claim that would need verification, that microbes can go into that wait state as a colony. They're not the individual cells may die, and then be reanimated 100 million years later under suitable conditions. That breaks a record. There was a claim of this from researchers at the University of Las Vegas in Nevada of about a 22 million year old microbe that they reanimated, and that got peer reviewed. So there have been claims for tens of millions of years being able to take microbes that went into suspended animation essentially and reanimate them. The 100 million is pretty long. Now the implication for this, rather beyond the time that this microbe has existed and could be reanimated, is that it implies life is very sturdy, and throughout space and in extreme environments, life, can handle tough conditions and then bounce back when the conditions change. And that's a big lesson for life in the universe, if that is the case. It's also a possibility that life could travel through space inside rocks like meteors or comets, and possibly travel even between star systems, because it would take tens of millions of years for a space rock to travel from our solar system, where it was ejected by an impact, say, to another solar system. And that raises the possibility of what's called panspermia, which is the idea that life seeded between star systems. That's been considered extremely unlikely in the past, but this discovery puts it back on the table.
The next question is from Predrag Ivosev, who sent an email asking, given that the Earth's magnetic pole has reversed in the past and is moving away from the North Pole now, what would happen when it reverses, or when the magnetic pole gets around the equator? Can you talk about how that process happens and how long it takes?
Yeah, I mean, the sun goes through a solar cycle, and the Earth goes through a magnetic cycle, because the Earth, it has a magnetized core. The nickel iron core has a solid part and a liquid part, and in the dynamic molten part, there's a dynamo mechanism that builds up the magnetic field. And because it has a differentially rotating core relative to the rate at which the planet is spinning, that magnetic pole does migrate. I mean, the magnetic field lines are obviously trapped inside the solid rock at some level, but they can slowly migrate through the rock. The actual mechanism by which the Earth's field flips episodically, and it's not at an absolutely fixed interval, hasn't happened for quite a while, is not really known. It's not fully known. It's very hard to model that kind of geochemistry, because it is geochemistry at some level. So this is one of these sort of still uncertain areas. Now we know that it does happen, however, because it's easy to look for mineral grains that carry magnetic fields, and we can see how the alignment of the magnetic grains in strata through the Earth has flipped episodically, and so we can see in core samples and in magnetic minerals the reversal of the Earth's magnetic field. But the mechanism by which it actually happens, or what the trigger point is not clear. Also, the migration of the magnetic pole is an interesting thing too. There are maps, you can find them online, that show how the north magnetic pole of the Earth, which we've tracked more carefully than the south one, has meandered over hundreds of miles over the last few centuries. So it's moving actually fairly fast. It's not headed to the equator as far as we can tell. It's sort of doing big looping circle around in the polar region. But the rate at which it does that, because it's not constant, is also not very clear. So there's some serious mysteries still about the Earth's magnetic field.
The next question is from World of Science, who's on with us live. According to some scientists, dark matter is like an exotic form of matter opposing gravity, like two different energy fields inverse to each other. So can you talk about the nature of these things, how they could possibly work? And then the last part of the question is dark matter responsible for the big freeze? I'm not entirely sure what they're referring to, but maybe you'll be more familiar with that.
Yeah, I'm also not clear about the last part, but the dark matter scenarios that people are thinking are most plausible now are still that dark matter is a new form of subatomic fundamental particle, an extension to the standard model of particle physics. The standard model of particle physics is the schema that involves 3 families of quarks and 3 families of leptons, light particles, and is cemented, this standard model, by the discovery of the Higgs boson 5 or 6 years ago. So that's the standard model, and dark matter doesn't have a place in the standard model. So whatever dark matter is, it's a massive, weakly interacting subatomic particle, and there are some candidates in theoretical speculations about extensions to the standard model. It's not, so the energy state of the dark matter particle is uncertain, which is to say its mass is uncertain. All we know about it is it would not have interactions with the electromagnetic force, because we know it doesn't emit or absorb light, interacts very weakly with matter. And really, things have not progressed substantially in that regard for several years. What has progressed is that the physics experiments, mostly deep underground in mines, that have tried to home in on what the dark matter particle might be or not be, have progressed. They haven't succeeded in detecting it, but they've started to rule some things out. So the dark matter parameter space available and left by experiment is shrinking to a point where we may have a crisis in physics when there's no viable candidate, even in extensions to the standard model. I'm not sure what the big freeze refers to. Obviously, the Earth had a big freeze, snowball Earth. It probably has nothing to do with that. The universe, as it considers its accelerated expansion, will go into a super cold state. There's a big freeze that's heading for the universe, actually. As dark energy takes over, that's dark energy, not dark matter. So I don't really know what there's no freeze that I'm aware of that relates to dark matter. We're still homing in on what we hope is the particle that will explain how everything holds together in the universe.
All right, thank you very much, Chris. So there are a bunch of people online who are very interested in the topics of black holes, white holes, and wormholes. And since they're all kind of under a similar topic area, I thought maybe we could just address all of them, and you can talk about the difference between black holes, white holes, and wormholes, and kind of how they're related to each other and how they're different.
Mm-hmm. So black holes are a prediction of general relativity, and they're considered part of conventional astrophysics now, because we've understood the mechanisms by which black holes are created from the death of massive stars. We also know black holes form in the center of galaxies. Every galaxy has one, and those mechanisms are understood too. So nature makes black holes that range from a few times the mass of the sun up to a few tens of billions of times the mass of the sun. And the mechanisms by which they come into play, and also the mechanisms by which they either stay dark or are bright, because there's hot material near them are understood too. The mysteries about black holes relate to their internal properties, particularly is there a singularity, because we can't really understand a singularity that's predicted in black hole physics. There's also the possibility of what happens to the information that falls into a black hole, which creates a conflict with quantum theory, and that's not resolved. So black holes are known objects. They're exotic, but they're not mysterious in large part because general relativity has predicted them. White holes and wormholes are completely speculative, so I'll make a very clear distinction between black holes that are a conventional part of astrophysics, whose existence we can prove and understand, and white holes and wormholes, which we don't know that exist, and they're speculated from general relativity, but until we have observations, we'll be very skeptical. In principle, a white hole is this, you might think of it as the opposite of a black hole. If a black hole is a place where nothing can escape, a pinched off region of space-time, a white hole is a region of space-time separate from our universe that's somehow emitting energy or particles. So it's opposite properties to a black hole. Now that's a pretty puzzling concept in relativity. And although mathematically you can make a white hole out of general relativity theory, it is extremely doubtful. So I will be very clear. Most theorists are very skeptical that nature makes white holes. There's just no mechanism by which we think they can be created. Wormholes are in another category because wormholes are also plausible in terms of general relativity. They don't exist outside the theory, but they talk about a situation where somehow two widely separated regions of space-time, widely separated in space, are somehow pinched together and connected. So we essentially get a tunnel or a portal between two regions of space that are connected by this wormhole. So that it requires space-time with particular curvature and particular geometry to create a wormhole. So you can draw a wormhole, you can imagine a wormhole somehow connecting two disparate regions of space through curved space-time. But again, the question is, does nature make this? Does nature do this? And at the moment, we'd probably have to say there's no sign that it does. Our universe, for example, is almost perfectly flat. So space-time in general, out there in space, between galaxies and within galaxies, is overwhelmingly space. So very unlikely that you have some highly curved, pinched space-time portal between two regions. Now, it can happen with dead stars. Dead stars, black holes that make a black hole. Maybe if two black holes form super close to each other, they might pinch together the space-time between them and make a wormhole between them. That's very speculative. So sorry to pour cold water on the questions that people like to ask about wormholes and white holes, but they are pure speculation at this point with no evidence for either.
Thank you. The next question is from Jim McLeod, who's on with us live. And the question is, why is a sodium laser the best wavelength for the adaptive optics technique? But because they do actually use other color lasers for adaptive optics, I thought maybe you could also expand on this and talk about why we would choose different color lasers to use for different adaptive optics techniques.
Right. So for adaptive optics, there are a couple of requirements. The hardest requirement, though, is the power requirement because, you know, the adaptive optics laser, what it's doing is it's sending a beam up into the upper atmosphere, into the layers where the turbulent motions happen that cause the distortion of an image. That's typically above the weather layer, so it's in the range from 10 to 20,000 feet up to 100 to 150,000 feet. So we're sending a laser well up into the upper atmosphere and needing enough reflected laser light back to be able to measure the wavefront and how it's changing in real time. So that's a laser that has to travel quite a long distance, and you have to collect enough of the reflected laser light to do the adaptive optics experiment. Because remember, you have to measure this wavefront changing many times a second, typically like 50 or 100 hertz, so 50 or 100 times a second. So the power requirement on the laser is quite intense. And so that's probably the main reason sodium lasers are used, because the technology to make sodium lasers of powers like 100 watts that's a pretty powerful sodium laser. I mean, it's definitely a dangerous laser. If you were to shine it at someone, it would blind them and it wouldn't kill them, but it would blind them instantly. So these are quite hazardous lasers, and for instance, you would never want to shine them at an aircraft that was flying overhead, and precautions are taken so that that can't happen. That's the primary reason. Also, you want a laser whose light is in the middle of the range of wavelength that you're studying, because the variations because how the atmosphere is turbulent is wavelength dependent at some level. So a sodium laser has its light, in the green or middle part of the visible spectrum, and that's typically where you're taking your data. So while you could use redder lasers, there are redder lasers. It's cheaper to make red photons, and so you actually could get as much power, more power per buck. With a red laser, you don't want to do that because you're typically observing at shorter wavelengths. Towards the bluer end, the lasers are not as effective. It's hard to get them powerful. They scatter a lot, Rayleigh scattering off atmospheric and tiny particles, so you don't want to use that. So there's a sweet spot in the middle, and that points always to sodium.
Thank you. The next question is from Tom Story, who's on live. If the Big Bang started as a singularity, wouldn't inflation contradict general relativity? It seems that time should run infinitely slowly. Is this a possible way that dark energy fits into cosmology?
So it's an interesting question, but the basic thing we have to remember is that inflation is not a part of general relativity. It's not really connected to the theory. So looking for consistency between inflation and general relativity is not something we can do right now, unfortunately. To put it another way, general relativity does not explain or account for inflation. Inflation is a mechanism beyond the theory of gravity that we have right now. And that's a bit of a problem. That means we need a better version of a gravity theory that can deal with extraordinary small scales and energy densities. Inflation is driven by something called the inflaton field. That's the hypothetical field associated with the vacuums of space that drives a sort of endless e-folding of the infant universe to take it from far smaller than a proton up to macroscopic meter scales. And the nature of that inflaton field is also not understood, and it's also outside of general relativity. So I think the fundamental problem with speculating about inflation is that we don't have a gravity theory with which to understand it. And that really, I'm afraid, hasn't improved a lot in the last years. We've had the inflation theory. Inflation theory is almost 40 years old now. And our knowledge, our experimental constraint on the inflation mechanism and the field that caused it have not really improved much in 40 years.
All right, thank you very much. The next question is from one of our live viewers, Red Unleasher, would like to know, why is our solar system flat? I mean, why is it not a spherical shape and the planets orbit in spheres, since that's the way gravity works?
Mm-hmm. It could be. It's a possible scenario to create a solar system that doesn't have the geometry of ours. However, the basic mechanism of star and solar system formation is that the initial gas cloud that forms the star and planets is slightly rotating. Almost every gas cloud in the universe rotates slightly due to turbulence, basically. There's a turbulence theory that explains this. And then in the process of collapse, the small amount of rotation is amplified by the conservation of angular momentum. So that almost automatically explains why you can have a slightly rotating vast gas and dust cloud that collapses into a disk-like system with quite a lot of rotation and angular momentum. And the planets form out of that disk. So it's therefore almost automatic that the planets will orbit in a planar geometry, in our case, in the ecliptic. Now, they do, of course, have slight tilt with regard to that. We know that the planets have tilts with respect to the ecliptic, which is the sort of Sun-Earth plane defined by the Earth's orbit of the Sun by 4 or 5 degrees. But that generally, they're quite planar. Interestingly, there are a few exoplanet systems where the planets have been found to have high ellipticities and are even counter. You can have some that are rotating and some that are counter-rotating because their angles of inclination are so varied. So nature apparently has made solar systems elsewhere that maybe don't have a spherical geometry but are quite different from our very carefully planar geometry. But ours is a very regular solar system in that regard.
So another sort of related question is from Janny C. Can you explain a little bit more about how the cloud of dust and gas for our solar system started to collapse? They're wondering where the gravity came from, but how does that build up, and how does that process even begin to at the start?
So there are two simple answers to why the solar nebula, as we call it, collapsed to form the sun and the planets and the other debris like comets and asteroids and so on. One is that it can just happen naturally. A large gas cloud can just very slowly evolve, and if it's in a finite region, of course, gravity is always going to go inward, and so it just may be a matter of time before it undergoes gravitational collapse. So it can start maybe with some rotation, so it's sort of rotationally supported, but not completely. And so a very small amount of initial inward motion of the mass will accentuate it. Remember, as something starts to contract gravitationally, the gravity strengthens and the pull increases, so it's a nonlinear process. So basically, one answer is it just happens slowly and then accelerates. The other answer that may apply to our solar system is it could be triggered. It could be kicked into collapsing. And there's an argument being made, and has been made, that our solar system is in that category. Now that will naturally happen in any active region of a galaxy, like the region around the Milky Way disk, where stars are being born and dying all the time. So a dying star, supernovae, that supernova shell, if it hits an incipient solar system or a gas cloud that hasn't started collapsing, it can push it into contraction. I mean, it's essentially going to compress it on one side, and that may increase the gravity enough to tilt it into gravitational collapse. The reason some people think that actually did happen in our case, that our solar system was triggered into collapse by a nearby dying star, is that we've seen deposited in meteoric material and outer solar system material radioactive elements that are only produced in supernovae with long decay times, so they still exist. That's very provocative evidence that our solar system, pristine, the earliest solar system material we can find, was seeded with radioactive material that we know to only be produced in supernovae.
The next question is from Ornab Sarkar, who's on with us live. So again, talking about the same kind of thing, but we're going to talk about it with galaxies now. Can you explain the theory behind the spiral arms of galaxies and why galaxies are flat like solar systems and how they form these spiral arms?
So the flattening of spiral galaxies is very analogous to the formation of a solar system, but on a much larger scale now. So now we're talking about a gas cloud that has hundreds of billions of times the mass of the sun and is vast, maybe hundreds of thousands or a million light years across. A long time ago, our galaxy first collapsed, we think about 11 billion years ago. So again, for the same reasons of turbulence theory, any of these super large gas clouds are also going to have slight rotation, and it's just a super amped up version of a solar system forming. The gas cloud starts to collapse. The collapse is preferential along the polar axis, the axis of rotation, and so you naturally end up with a disk. So you turn a large quasi-spherical gas distribution into a disk distribution. As the gas collapses towards the equator of that disk, of course, it's going to compress, and that compression will lead to star formation. So you naturally have star formation occurring in this disk that's now rotating. And so you've got some of the pieces of a spiral galaxy right away. There's a central region where there's just a more regular spherical distribution of stars that collapse spherically. And in our galaxy, that would be the bulge. And in any spiral galaxy, that's the bulge. The spiral arms are interesting because they have a slightly more sophisticated explanation than just the collapse itself. Once the disk starts to rotate, it rotates differentially. So obviously, the inner parts of the disk rotate a little faster than the outer parts, and so on. Rotation speed does increase going out, but then flattens off. And so the galaxy will tend to wind up. If you could think of a galaxy as being a spiral or any pattern, it will be winding up. And the interesting thing there is that if you do the math, our galaxy has rotated a few dozen times since it formed. And so if the spiral arms were just fixed patterns of stars, the galaxy would have wound so tightly that you'd never see the spiral arms, whereas we can see a small number, 2 or 3 or 4 spiral arms. So we know the spiral arms are not fixed patterns of stars that were there all the time, because the rotation of the galaxy would have wound them up so tightly that you'd never distinguish the spiral arms. So we think the spiral arms are a pattern rather than a fixed set of stars. In other words, the density in a region of space will increase and decreasing as a wave, where whatever stars are in that region of space are subject to a compression and then a rarefaction wave. And when the wave compresses, they will form stars and shine bright. When the wave passes through, it becomes less dense, and so star formation is suppressed. So we see star formation accentuated in the spiral arms because of this wave pattern that is going around, rather than the same stars being part of the pattern all the time. So it's a slightly more sophisticated explanation of spiral arms. They do trail the rotation of the galaxy, so you can't look at the direction the spiral arms wind and infer which way the galaxy is rotating. That part at least is intuitive.
Thank you. The next question is from Ashwarya, who would like to know if the Drake equation is just an assumption or if it's been practically proven.
The Drake equation it's neither an assumption nor has it been proven. I think even Frank Drake admitted that the Drake equation was sort of a container for ignorance, a way of organizing our thoughts in astrobiology. He did this in a very famous way. He was a young researcher at the National Radio Observatory in Charlottesville, Virginia. They gathered together a small set of people to talk about astrobiology. There were not many astrobiologists then. I think there were 24 people at the meeting, and that was most of the people working on it. Carl Sagan was one of those people, and so on. And as one of the local hosts at the radio observatory, Drake and a young postdoc, he just went to the board and wrote down the Drake equation pretty much in real time to help organize the discussion. So it's a set of factors that multiply together give the number of intelligent, communicable civilizations in the galaxy at any given time. And then the time or the lifetime of those civilizations is the last factor. So it is not a conventional equation, because you can't plug in numbers and get an answer, because 3 of the numbers in the Drake equation, 3 of the terms are known, measured by astronomy now, and 4 are unknown, and they're completely unknown. So when you multiply 3 numbers that you know by 4 numbers where you really don't know at all, then the answer is I don't know at all. So that's why Drake called it a container for ignorance. So I think it's more useful as a way to organize your thinking about life in the universe than as a way of generating a number that you can then go out and look for or test. And I think that's the way people think about it. However, fair to say that in 50 years, 1960 to 70 years, nobody's come up with a better way of organizing the ignorance than the Drake equation.
Thank you very much. The next couple questions, selected a few that are going to be about the topic of Mars and travel to Mars. So Diablo Code asks, now with SpaceX to the International Space Station passing the test, what are the challenges to having a mission to Mars? What makes it different than going to the moon?
So the challenges for Mars are just the scale and the cost and the hazard of the mission. So for SpaceX, this is 2 challenges. This is a technical challenge, and I think they're up for the technical challenge. They have a rocket design that is in principle able to transport hundreds of people or an enormous amount of cargo through the parts of the solar system that include Mars. It's Elon Musk's acronym for this is his BFR. It's his big expletive rocket. And it's just a super scaled up version of the rockets that he uses now, which have, I think, over a dozen or 13 of his biggest rocket engines instead of just one. So on the technical side, pretty clear that I think Musk and SpaceX can do this. But the cost is still enormous, and the hazard is enormous because, you know, the risks of failure and the cost in human life if one of these big spacecraft, you know, has a problem or can't return are huge. So and then the other problem or limitation or controlling factor, I would say, is finances. So this is going to be an expensive mission. It will not be self-funding in a sense. And so Musk actually has to move forward his business model for SpaceX before he has the resources to do the Mars mission. I think that's what's limiting him as much as anything else. SpaceX has done well with government contracts, such as the one that it recently fulfilled to send humans to the space station and return them successfully. It happened recently, and it's going to do that again. And these are multi-billion-dollar contracts, and SpaceX makes a significant profit from these contracts. So SpaceX does have a viable business model to help NASA launch American astronauts, but it's only going to start coining money when it sends tourists into space, rich people who can afford to pay. And it's going to need to do that for a few years before I think it even really has the resources to invest in a Mars mission. And really there we have to contrast Elon Musk's two major business activities. Tesla, with a lot of skepticism originally, has met its marks and is making profits quarter after quarter, including during the pandemic, which is remarkable. And it's obviously a bet for the future that is completely plausible because we know cars are going to go more and more electric over time. So even if he had to take early risk and losses, the Tesla business model is pretty secure based on the future of electric power and electric cars. The future, the bet he's making on Mars is not one with a big payoff at the end or in the middle. So he's going to have to sink a lot of money into it, and I think that's what's going to limit the time that it takes.
Thank you very much. Now, Oliver Crosby would like to know, how close is humanity to establishing a permanent human presence on Mars? But before that, I think we should address, how long do you think it will be before we actually get to Mars?
Right. Before humans get to Mars, you know, a good guess is 10 years at this point, and it could happen. You know, NASA and the American government, probably working collaboratively with other governments, does have a fairly cautious, staged approach to getting humans to Mars, not for a permanent colony, but we're just talking about getting there for the first time. And that's because it's done in stages to keep it low risk. And really, it's a coin toss whether Musk gets there first on his first exploratory missions. So I think less than 10 years for the first humans on Mars for a short visit to reconnaissance. That's a good bet. For a colony, 20 years to 25 years is a much safer bet because there are infrastructure required to keep even a minimal set of people that you would have to, you know, they're not going to be self-contained and live and die there and new generations there. We're not talking about that kind of a colony. We're just talking about a set of humans on Mars that stay there for substantial time, like years. That's a lot harder because the infrastructure needed to keep them safe is significant, and none of it exists, of course. You're building it from scratch because you can't transport everything from the Earth. It's too expensive, too heavy. So you have to essentially mine the Martian soil to make building materials and to generate rocket fuel and to get water. And you have to do a lot of stuff locally, which means you've got to build the capacity to do that locally. And that's going to take a while. So I would give 20 years as that's an aggressive timescale for having a human colony on Mars.
The next question, Mars related, is from Ike, who is on with us live. Is it a good idea to go to Mars where the radiation is incredibly high? What are the risks of sending humans to Mars?
Yes, the risks are substantial. There's the risks of the journey, which is about an 8-month journey. That's the fastest. And if you saved energy, it might take more like a year. So you've got a year in space there and back, assuming you come back. And I think the calculations say that in an 8 month journey, the minimum journey to Mars, you experience more than a lifetime in a normal spacecraft that people would be using, which can't be heavily shielded because it can't be too heavy. You experience a lifetime's worth of radiation exposure in 8 months. So that's a lot, but it's an adventure of a lifetime, so that's not considered impossible. But once you're on Mars, of course, staying for a longer time, Mars has no magnetic field, and so the radiation exposure, potentially cosmic rays and so on, is also substantial. So basically, the Mars habitats that people are designing or planning are heavily shielded. And they're not going to look like these wonderful bubble domes, translucent domes, where you just get to see all these vistas in all directions of the Martian landscape. Almost certainly, they're going to mine the Martian soil to make slump block. That's the best way to think of it, because that's actually what you fire up with a building plant on Mars. And so it's going to be an igloo covered with hardened slump block, and there'll be maybe small ports to look out over, small access apertures, but it's going to be a sealed unit. And with that amount of shielding, then you can keep the radiation dose tolerable.
Excellent. Thank you very much. The next question is, is the water on Mars similar to the water on Earth? And could we drink it even though it's more salty and it has all these other things in it? Can you talk about water on Mars?
Sure. Water on Mars is going to be not potable typically where it comes from, just like water on a lot of places on the Earth in desert or marshy situations is not potable because it either has microbes, that's a problem Mars probably won't have, or it's brackish or heavily full of dissolved solids. So yes, Martian water will be heavily filtered probably with ion exchangers to remove materials and purify it. I don't imagine there's purely drinking water anywhere on Mars, just like there's not really that much pure drinking water even on the Earth.
All right, the next question is, water has been detected, or the history of water has been detected on the land of Mars, but there's also some evidence that there were oceans on Mars. Is it possible that life on Mars exists, but we just can't detect it right now?
It's certainly possible. So that the evidence, the cumulative evidence that Mars was covered with shallow seas probably 3 to 2 billion years ago, and then they dried out, is pretty strong. It's very strong. It's based on geology, geochemistry, and the morphology. You can just see what look like shallow seas and lake beds and so on. But that was a long time ago. Now, there could be fossilized microbes that are detectable in that, and J0 crater, the one that Perseverance is headed towards, is a place that we think was underwater some while ago, so it's a very promising place to do that sort of archaeology. As far as microbes that are currently alive on Mars right now, the only possible place that could be is fairly deep underground, not super deep. There's very likely aquifers, currently liquid water aquifers under the Martian regolith or topsoil. They're almost certain to be tens of meters, maybe hundreds of meters below the surface, and that's not any distance we can drill with any of the missions that are planned or in the near term. So getting to that life, even if it still exists, is really difficult. It's beyond our capabilities right now unless we develop a pretty new type of space probe.
All right, moving on from the topic of Mars, Media Slate would like to know, is it possible to send probes on comets and use the comets to exit the solar system? Would it be possible with a human space probe?
That's an interesting idea. So we know we have Earth crossing orbits for comets. So we have comets that come into the inner solar system and then head far out. Halley's Comet is a classic example, every 86 years. And so could we hitch a ride on a comet? Now, the comet won't leave the solar system. Comets are bound objects in the solar system, but they do progress in that outer extents of their orbits to 50 to 100,000 astronomical units. And that's that's a lot. That's 1,000 times the distance to the outermost planet. So to all intents and purposes, it's very close to interstellar space. It's well beyond the orbit of the planets by a long factor. So yes, in principle, we do have the technology to sort of hitchhike on a comet as it's passing through the inner solar system. We'd have to match its speed and trajectory, and it's going quite fast, but that can be done actually with our technology. And then you could tether to it and drill into it and, you know, attach to it with a habitat. I mean, you could have people there too. The problem is really time, because while the comets are moving fast and you know, they are slowing down as they move outer into their orbits, according to Kepler's law. So Halley's Comet is a good example. Halley's Comet does not go out to 50,000 AU. Halley's Comet is a really inner solar system comet. If you wanted to pick one of the comets that's going to get you well outside the planets by a factor of 10 or 20, now you're talking about long period comets. And long period comets means you're going to have to stay the course for thousands, hundreds, for sure hundreds, and maybe even thousands of years to get to the outer solar system, and then you're slowing down all the time as you head out. So it would be a rather long, frustrating voyage.
The next question is from legit gamers who would like to know, why is there more matter than antimatter in the universe?
We don't completely know, but the best guess is that the profound asymmetry between matter and antimatter, to the point where there's just hardly any antimatter. We can create it fleetingly in labs and accelerators, but tiny, tiny quantities, and then it disappears almost immediately by hitting matter and going away in radiation burst. The best reason is to do with the unification of three of the forces of nature, grand unified theories, which unify the electric, weak, and strong forces of nature. They have mechanisms whereby you can generate what's called baryon asymmetry. So heavy particles in particle physics are called baryons, and baryon asymmetry is the excess of baryons over antibaryons, protons over antiprotons, neutrons over antineutrons, etc. So it's built into the conditions that pertain when these three forces were unified, and there was symmetry. So in the unification scenario, the natural state of a unified theory is equal amounts of matter and antimatter. It's actually generally a law of physics that matter and antimatter balance out in particle interactions. But if there's a slight skewness in this symmetry, so it's not a perfect symmetry at the time of the grand unified forces starting to freeze out, then you set up a scenario where the matter and the antimatter mostly annihilate, leaving behind a lot of photons and a tiny little residue of matter. So the very broad brushstrokes of the mechanism are known, but the actual details of the mechanism depend on grand unified theory that we don't really have right now. So it's still speculative.
All right, I did forget one question about Mars, so we're going to jump back there. Both Chris and Kadambini Chaubi have asked what your opinion on the Perseverance mission is that was recently launched. Can you talk about what it is and what its goals are and its limitations to start off with, and then I'll continue with another one.
Perseverance is the follow-up to the Curiosity rover that's still working on Mars. And it's a twin, so they obviously save money by twinning the rover, and it was originally called Mars 2020, but it missed its 2020 launch window to get to Mars in 2020, so it's going to be 2 years later, and it's just left. It's got a dedicated suite of instruments, 8 or 9 instruments, and of course the technology has progressed since the first rover, so it's got some pretty sophisticated instruments. It's a little short on what we would call pure life detection instruments. It doesn't have a PCR reactor, polymer chain reaction for taking tiny amounts of DNA and amplifying them, and so looking for DNA directly on Mars. It's not going to do sort of grandiose and exciting and ambitious experiments like that, because the truth is they're most unlikely to succeed. So what it's going to do is move the bar forward, move the field forward in terms of nailing down the likelihood that the Martian habitat hosted microbial life in the past when Mars was warmer or wetter. And it's going to do that through geochemistry, essentially, not through biology. And it's pretty impressive instrumentation. So it should start to paint a picture now of Mars as a formerly habitable planet where we acknowledge that the microbes could still exist under the surface. And it's in a it's going to a great place. J0 crater is it's better than Gale crater at some level because the geochemistry makes it extremely likely that this was not just a place which was potentially habitable, but it had the right pH and the right chemical balance, that it would almost have been unlikely, if there were water there, that there were not microbes evolving there. So that's pretty exciting, and it again has better instrumentation to do the same kind of work. But it's an extension of what the Curiosity rover did. It's not some radical re-envisaging of a Mars rover to do just life detection experiments. We're not there yet.
All right, and then a kind of a follow-up question about the Perseverance rover is, what is your opinion on the mission? Do you think that Mars is given unnecessary importance in the kind of suite of astronomy and Earth science exploration?
There's an argument to be made for that. I'm influenced by some of my colleagues at the Lunar and Planetary Lab, so I'm in astronomy here at Arizona, but across the street, the Lunar and Planetary Lab is, I think, along with the Caltech department, one of the two biggest planetary science academic departments in the world. A lot of planetary scientists, dozens of faculty and dozens of researchers, and a number of them work in the outer solar system, and they feel that targets like Titan and Europa and Enceladus and so on have been slighted or neglected with the obsession on Mars. So the obsession on Mars is real, and there's clearly a strong focus on that, and that comes from NASA. It also comes from the practicality that it's an easier location to get to. Outer solar system missions take minimum of a decade and a minimum of $1 billion. On Mars, you can definitely do it quicker and you can do it cheaper. Although the Perseverance rover is not cheaper. It's way over $1 billion. But the two in Spirit and Opportunity were less than $1 billion, for example. So I think people put emphasis on Mars because we have such strong evidence that it was possibly habitable a few billion years ago, formerly habitable planet, and we just can't say that about anywhere else with that confidence. Because it's close, because you can get there in a year or so rather than a decade, and because there's a long-term intention to send humans there, whereas we're unlikely to have colonists on Titan or Europa. So it plays into a longer-term strategy of planetary exploration. And so I do agree that it gets slightly obsessive level of attention, but I think given the infancy still of our exploration of the solar system, that's sort of understandable.
Thank you very much. The next question is from one of our online viewers who would like to know if the human species, do you think, can be transported to some other suitable planet? Will we be able to go just as we are, or do you think we'll need to genetically modify ourselves? What do you think the future is of humanity beyond Earth?
I think, I hope we make the Earth work. It's our best bet. Living off Earth for more than a tiny number of people is always going to be hard, expensive, and beyond reach. So we're talking about, 7 billion people on this planet, and so with very great certainty, our best bet is to take care of the Earth. So that's my general feeling on the whole thing. As far as what might happen of moving off Earth, I think we will move off Earth. I think an offshoot of humanity will eventually take root on Mars and the Moon maybe, and maybe other places, maybe head off towards the stars in suspended animation to see what happens. What it would require is, yes, it would require retooling of the organism. We're going to, and it would probably require genetic engineering technologies to make us sturdier against radiation. to make us sturdier in a weak gravity environment, such as we have on Mars and even more strongly on the Moon. And those technologies are evolving pretty fast. So I think off-Earth colonists will use aggressive genetic engineering and modification techniques. They'll also use engineering of their bodies. They'll actually, use replacement of body parts and augmenting of human capabilities with machines and robotics. It's slightly scary, visionary stuff, but I think that's the kind of people that are going to do this experiment. But really, it's only ever going to impact this tiniest fraction of humanity. Most people will just be left to look and wonder about it. The idea of us leaving the Earth en masse is just simply not realistic.
And I think, so we'll take two more questions. The next question is from one of our live viewers who would like to know what your thoughts are on the universe as some kind of consciousness. What are your thoughts on the idea that the universe is either conscious itself or forms some kind of greater consciousness?
So it's an interesting question, and it comes up in speculation in the literature and more fantasy and science fiction literature quite a lot. The idea that inanimate matter, which is what the universe is, could have consciousness on a huge scale would be an extraordinary supposition. And unfortunately, there's no basis for it. And the real reason for that is that the universe as a whole, in large scale, or as a total, does not have sufficient organization to imagine that something which has organization like consciousness, because even if we don't know how consciousness works, we understand that it involves pattern and organization at some level. The universe as a whole does not have such organization built into it. It's governed by random chaotic forces that we pretty much understand. And so there's no sign that there's any pattern or organizing principle out there in the universe onto which consciousness could attach or from which it could emerge.
All right. The next and final question for today is from Theolock. What are your views on the SpaceX Starlink satellites? There are a lot of people who are very upset about them and are not convinced that any of the mitigations that they're claiming will help. But there are also all sorts of promises for what the internet access they'll be able to provide. What do you think on both the astronomy and the practical uses?
Yeah, that's a controversial topic among astronomers. I was at the before we were all locked down from traveling to meetings. I went to the American Astronomical Society meeting in Hawaii in January, and I was part of a special session on the Starlink satellites and other satellites. That's not the only set of satellites that are coming in large numbers to the skies for telecommunication purposes. So I was there giving a perspective on the space program. There was a SpaceX representative there, a pretty senior person, Elon Musk. And astronomers were talking about the impacts on their field, and there's since been a number of papers. And the impacts are substantial. I mean, in the end, these will be tens of thousands of low Earth orbit reflective objects that are readily apparent to the naked eye sometimes, just before, they're around dusk, beginning and end of the night. So they're not throughout the night that you can see them this way. But they're huge numbers, and they're non-trivially bright. Simulations by people with the Large Synoptic Survey Telescope, which is probably the most impacted of our next generation facilities. It's going to do all sky surveys to Hubble depth every few nights. These simulations indicate that it will be quite massively affected by this, that these satellite trails will litter most of its science frames and lead to serious problems for that project. SpaceX has responded to the questions and criticism and has tested a modified more opaque or matte reflective coating to try and reduce the reflectance of the satellites. The jury's, I think, still out on how effective that changed coating has been, but they're not deviating their course. They're committed. They have their own commercial reasons for going forward. So they are talking to astronomers and consulting with them, and and engaging in a dialogue. But I don't think when push comes to shove, they're going to stop doing what they do, or the other companies, because of this. So I think at the moment it's at the level of a pretty significant threat to deep sky research astronomy. On the other hand, and on the other side, I'm an astronomer, but you have to look at both sides. And then SpaceX is driven by the profit motive. It's a company, of course, they want to make money. But the niche they're attending to is a substantial niche. It's the fact that a large part of the developing world does not have cheap, high-speed internet. And so with these legions of satellites, tens of thousands of them in low Earth orbit, I mean, such a low Earth orbit that they degrade and fall out of the sky and you have to keep replacing them, but there's many of them and they're cheap to make, each one. This will, in principle, remove the digital divide that exists between the developing world and the rich world as far as broadband and wireless internet. And that's a powerful force for good, for economic development, for education, for things that I care about. So I can see the good in that. And so it's a tricky situation. Astronomers' worst dreams will probably not, nightmares will not probably come to pass, because these companies will do their very best to make the satellites dark, but they're not going to stop these projects. That's pretty clear. So thanks very much for all your questions, from cosmology to SpaceX satellites in near Earth orbit. And we'll be back with you on a weekly schedule. We'll announce the next few sessions in a day or so. Thanks very much, and thanks to Matthew and Alexander for facilitating.
Thank you, Chris. And the final thing I want to mention to everyone is that we now have a Discord server for people who are interested in joining our community of astronomy enthusiasts, and people who are in a class and not in the class are welcome to join. There's a link for the Discord in the description, so make sure you check that out.